Okay, good morning, everyone. So I'm Rabian Wangkeeree from Northern University. Today I'm going to talk about the neurodynamics framework for the generalized pinball uh, SVM. In this work, we also show you about the convergent analysis and also some application on the medical imaging application at the end. So in this work, I joined with my college from the Northern University. So uh, the next, let me mention about the plans for this talk. I will start from the motivation. I will start from the motivation, why we use the right Pinball-Loss and why we use the neurodynamics and continuous time model. And then I will mention about the main contribution of this talk. So the first one I want to mention about the smoothing agnostic model, like the traditional model, like the existing model, like the previous model, right? And the next thing is that I want to mention about the proposed model, name complex suppose that smoothing model. In this model, we try to give you some new class of the smoothing function to approximate the non-smooth function on the SVM module. And then we try to study about some theory about the error bar. We try to see some the error bar. We try to prove some the consistency. We try to show you about the stability analysis, like the asymptotic Lyapunov stability or exponentially stability. And then we try to show you about some the extra experiment on some data because we are working on the machine learning model. Then we try to apply this model to make the to solve some problem like the classification problem, like the binary classification problem. And the final part of this talk, I want to show you about some application to the real image on the MRI bond material density problem. So uh, first of all, I want to mention about some of the very important loss function in the machine learning model, namely the Hing loss function. As you know, the Hing loss function defined by the this formulation, like the maximum, you take the maximum between the 0 and V, because V is coming from this formulation, like try to compare the difference between 1 and the predicted value here. So for the Hing loss function here, and then it gives you some very advantage like the sparsity and and then lose some issue, right? As you know about the story of the Hing loss function, like it's really sensitive to the noisy data, because suppose that if you have the noisy data and then you try to solve this problem by using this noisy data, by using the Hing loss function, maybe in some situation, this loss function is really sensitive to the noisy data, and also some the situation maybe this loss function is really unstable under the stamping techniques, right? So in the next loss function proposed by Professor Huang, namely the pinball loss function. In the this loss function, the main concept for this loss function is like that they try to penalize the every simple, right? And then they get some really advantage about the low net of this model implemented by using the pinball loss function. This model is really low bus, but they lose some disadvantage some this for this loss function, like they lose some the sparsity. That is really some issue, some big issue for this pinball loss function. So in and then they try to give you they try to restore the sparsity for pinball loss function. That's why they try to give some new loss function like the epsilon intensity pinball loss function. They try to give some brand to some zero loss band for the pinball loss function. So this is the if you look at this picture carefully, you can see the different how different between all of these loss function. And finally, this loss function attended to the generalized pinball loss function. Like that, they have the two different. You can give the different slope tau 1 and tau 2, like this way, and then you have more the epsilon 1 and epsilon 2 to for this loss function. That this loss function you can see in here, like this way, right? This is the visualization for the generalized pinball loss function. So from this idea, if you look at the generalized pinball loss function carefully, you can observe that for the for for the omega here and c divided by this way and v divided by this way. So if you look at here carefully, so you can see the component of the generalized pinball loss function, like they try to add some to term in this loss function, like they try to you can write down the generalized pinball loss function by using the pass function defined by this way, right? It's because as you know that this function, you know that this function is pass function, like the maximum between 0 and x here, and then you can define the generalized pinball loss function by using this pass function, and then you define by this way, and then if you go back to the generalized pinball SVM, then this is the objective function for the generalized pinball SVM, right? And you add more the regularization term in here, and then this is the sum of the loss of the this module, and this is the loss function, right? This is the generalized pinball loss function defined by this way. So this is the objective function for generalized pinball SVM defined by this way. So if you look at here carefully, so you can see that the generalized pinball loss function here is a piecewise linear contrast, right? And then it means that this function is non-smooth function, right? And you can see the king for this loss function. If you go back to the previous visualization, you can see this is the king for this generalized pinball loss function. It means this loss function is non-smooth loss function, right? So if you this is a non-smooth loss function, and then it means that its gradient is undefined on the king. Everyone know about this one, and it means that if you try to solve this problem by using the gradient based optimizer, it's impossible, right? Because this function is non-smooth loss function, and then and also if you try to use like a contrast time solver from the ODE system to apply to this loss function, it's possible, right? Because this function, I mean this objective function, is not smooth function, right? So in our problem is the contribution of this work is about we try to give you some smoothing techniques, and we try to solve this one by using like the neurodynamics method. So, okay, so the first one is that we try to replace the pass function in the generalized pinball loss function by using the differentiable function here depend on the some parameter mu, and as you increase the mu to infinity, and then we can recover the pass function. This is the idea in this contribution of this talk. So after that, after we have the smoothing module in the SVM, And then we try to solve this model by using like the neurodynamics uh, algorithm, like the RNN uh, paradigm, right? So in this, how to do in this idea. So it means that we try to share from the original problem. We can write down in the ODE system, right? In the ODE system here, we try to prove that the equilibrium point of the ODE system are the same with the optimizer of the traditional uh, uh, problem, right? And then we try to study more about the behavior of the trajectory of the solution of the ODE system, right? If you want to uh, know more detail about this idea, you can go back to this work, right? It's okay. So and the previous work, if you go back to this work, they have also the smoothing techniques for solving this problem, like in this work, right? So they try to give you some the technique about they try to replace the the plus function here by using the hyperbolic tan function. Just only the hyperbolic tan function, right? Only one function, which is the only one smoothing function. But in this work, they still have some disadvantage, something like the try to one transcendental function. This is some limitation for the existing work. So and also, if you look at in the second limitation for this work, like suppose if you try to compute the derivative of this new smoothing function here, and then this derivative here is never be zero. It means they still have the zero every simple point, every simple support vector, right? So this is some limitation for this model. So if you look at carefully, so you can see the 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 derivative here is never exact to the original general pinball loss function. It's never exactly equal to the generalized pinball loss function. This is some limitation for this work. So in this work, uh, we try to solve these three issues from this work. So that's why we try to give some the smoothing technique here. And this is some contribution for this work. The first one, we try to rehash, we try to let you know about the smoothings X notice model. We rehash instead of the only one 10 hyperbolic 10 function, and then we try to give some the generic admissible class of the function. And then we try to show some the existent theorem. We can show you about the uniqueness and stability for the entire admissible class of this function. And the second contribution is that we try to use the function proposed by these two works. Very important function, right? We call this function like a compactly support that instant. And then we try to introduce the new SVM by using this smoothing function is coming from these two works here. And this is really advantage if you try to use the function from this work. So, and finally, we try to after we introduce this model, and then we try to use this model. We try to study many concepts here. It's like the Lyapunov the stability. We try to show you about the Gobori asymptotic and exponential stability for our model. And after we have a study about the theoretical results, and then we try to use this model for solving some the UCI data, because we are using the binary classification model like the SVM. And then we try to use this model for solving the data from the UCI. And then final part of this work is that we try to use this model for solving the real data from the hospital. So this is uh, the class of the admissible smoothing function. We try to introduce this is the class of admissible smoothing function. Suppose that if you have the function phi, and this function satisfied all of these condition. I mean the S1 to S5 here, and then we call this function, this class of function like the admissible smoothing function. For example, for the S1 here, and you can see this function is belong to the C1. It means the continuously differentiable in the first component. This one. And for the second property here, you try to see the difference between the distance between the smoothing function and the path function. You want to see that you want to see the distance between the traditional one and the smoothing one. How far the smoothing one from the original one. You can control by this some constant here, and so on, right? So it means that if you have the function satisfy all of these property, and then you can call this function is a admissible smoothing function. So okay, we try to the next thing is that we try to check. Suppose you have the function, and then you want to check that this function is an admissible smoothing function. You have to check all of these property. So okay. And after you have that, so the next thing is that suppose we this is as you remember this function. This is the objective function for our problem, right? Because you as you look at here carefully, you can see that we replace the path function by using the smoothing function here. This is our smoothing function. In the original one, here, this is the path function, right? This is the path function like this way. So we try to replace the path function by using the smoothing function. So this is our objective function here. So after you have the objective function here, and then you can try to write down the ODE system. Later, you try to compute the derivative of the omega t with respect to t by equal to kappa and phi t, phi omega. By this, how to know this one? This one later you try to compute the gradient of this smoothing function, right? Because you take the gradient of this function first, and negative gradient of this function equal to phi omega. So this is very easy, right? Suppose you want to compute the gradient of this function, you can get this vector. So this is our networks, our gradient flow for this network. Suppose that if you go back to the existing model, you can see that if you take the field divided by this way, you can recover the previous 10-ish model, right, on the special case. So so the next thing is that how to see some example for our smoothing function. So if you go back to this work, Shang, and the work from this paper, you can see the definition of this function. You can see definition of this function. Later, you try to approximate approximate the path function by using the polynomial function, by using the some polynomial function here in this band, right? So if you define this function by this way, it means you can prove in this paper, right? You can prove in the previous paper. You can prove that this function is a smoothing function for the path function. Okay. Also this function. Also this function. You can prove that this function is a smoothing function for the smoothing approximating function for the path function. It's okay. The next thing is that we try to see about some advantage of these two functions, because if you look at the number of the if you look at here carefully, so you can see that this is the 10th function, right? So if you I show you that the gradient for each never zero for the hyperbolic 10 function. But if you look at here carefully, you can see that the gradient allow this area equal to 1, and the gradient allow this point here equal to 1. The gradient here equal to 0, right? And the gradient at point allow here equal to 1. Very simple to compute the gradient of this function. And then if you try to see the percentage about the gradient 0 for these two functions, you can see this one. If you try to compute by using some data, right? This is the orange one here is from the data A, and the blue one here is coming from the data WDBC here. So, okay, this is some. It means if you use these two functions, you can get higher number of the zero gradients for this function. It's okay. The next one is that we try to compute the distance between the original one and the approximating one, right? We can prove that the distance here is greater than or equal to this some small number here. That's why that's mean that you can get the upper bound for the distance between the original one and the smoothing one this way. So, and after that, we try to show you about the convergent analysis. It means like you can prove that the equilibrium convert to the minimizer of the x-axis non-smooth Generalized Pinball-Loss SVM. You can prove this property. It's a very important property here. So the next thing is that if you want to introduce some, you want to study about the globally asymptotic asymptotic stability and exponentially stability, you have to introduce some Lyapunov function. This is the our Lyapunov function defined by this defined by this way, like the composite between this one and this one. We have two terms in this Lyapunov function, and then after we have the Lyapunov function, and then we can prove that the equilibrium point, which means the omega star here is the Lyapunov, and also the globally asymptotic score stable. So, okay, and then we can prove that the distance between the about the state decay. So it means the norm of the omega t and equilibrium point less than or equal to this one. So, okay, later we get the state decay for this function, for this trajectory. So, and the first one is that we try to study about the residual decay. It means we can prove that the norm of the gradient of our objective function is less than or equal to this one. And also we have this property, and also we have also this some property here. It's okay. That's it. All of these result we can prove in this way. And it was also okay. Let me skip this one. So the important is that after you have the study about the theoretical result for our problem, and because our problem focus on the later how to get more capacity for the hours model, that's why we try to solve some this problem. If you look at here carefully, so we try to check some uh, we try to use the hours model for solving the some data. Like we have two data A and data B here. So okay, W D B C. So and then we try to see uh, about the sparsity issue for each problem. So if you compare here in this table carefully, so you can see if you look at here carefully, so you can see you can get higher number of the sparsity, right? So this is the like a percentage of the sparsity for the hours module proposed by using these two smoothing function. So after that, so after you try to solve with the synthetic data, because in if you look at here carefully, so you can see this synthetic data, right? So after that, we try to uh, solve some classification problem in SVM with the 6 UCI dataset, and then we try to average. We try to compute the average, the mean accuracy, and we try to give the length for the module, and then we found that this model is very good model, right? It means like you can get higher accuracy, and then you can get the small rank here. It's small, it means is the better, right? So if you get the small rank, it means you can get the very high performance for that module. So okay. And then if you try to see the comparison between your model and the traditional one in SVM model, and then you can it's like you can get very good model here if you try to compare between the accuracy between all of them here, and then you can get very good model here. So the next thing is that we try to uh, the next thing is that we try to show you some application in the real data, because in the real data here we try to collect the data from the Norwegian University Hospital, and then we try to solve this data. I mean, we want to make the application for this data by using our model. But the challenge for this application is that we have the very small number of the data here, right? We have just only 194 number of the data, but and then you can get some performance you can see here, right? We can get a lot the AUC a lot 77.7%. This is it looks so good if you compare with the number of data equal to 194 data here. So this is if you try to compare our model and the existing classical model, and then this is the ours performance, and then you can see this is the ours performance. It looks so good, right? If you compare with some existing model. So okay. So okay, that's all of my works. Okay, thank you very much.